Hello everybody, so in this video we are going to talk about an applied example of antiderivatives. Okay, so in this example it says a stone is dropped from the upper observation deck of the CN tower about 450 meters above the ground. Okay, now before we even talk about what we're going to do in this example, we need a couple of pieces of information. Okay, so one thing is that we need to know the acceleration that just comes from a falling object with the gravity on Earth. Okay, so this would be 9.8 meters per second squared, or if you're talking about feet per second, it is 16 feet per second squared. Okay, so now let's talk about what we are going to do in this question. Okay. Okay, so we are going to talk about finding the equation for the height of the stone above the ground. So I want to review the relationship between acceleration, velocity, and position. Okay, now if we're talking about position, which in this case is height, if we take the derivative of that, right, this is the rate of change of the height. So this is going to be the speed, or more accurately, the velocity. Okay? And then if we take the derivative of that, right, talking about how the velocity changes over time, that is the definition of the acceleration. Okay? So what we're going to use here, right, is that we know the acceleration because it's only due to gravity, and we are going to take the antiderivative to find the position. Okay, so we are going to start with what we know, which is that the second derivative is going to be the acceleration due to gravity, 9.8. Okay, now when we talk about the acceleration, it's going down, so we put a negative sign to show that it's going down. Okay, so let's look at, so this is the second derivative, right, or the acceleration of the stone. Okay, so let's look at the antiderivative, right, which would be the first derivative. Okay, so we're starting here at the acceleration and we're going backwards, right? So if we look at the first derivative, f prime of x, right, this is going to be the velocity function, right, which tells us the speed. Okay, so again, if we have just a number, remember that is going to come from having x, right? When we take the derivative of like a times x, we just get a. So that's why when we take the antiderivative, we get that number times x, and we still have our constant. We don't know what that is. Okay, now we really want to figure out what that constant is, so we are going to use this information here. Now, if it says that it is dropped, okay, this is physics code for the velocity at the start is 0, okay? No starting velocity. Right? Remember, velocity is just speed with direction. So if it says it's dropped, that means it has no starting velocity. Okay, so we would have that f prime of 0 is minus 9.8 times 0 plus c, okay? And we know that this should be 0. So our c value is 0. So this tells us that our velocity function, which is our first derivative, is minus 9.8x, and then we don't need to put plus 0. Okay, so now we want to look at our original function, right? Our position function, right? This is the first derivative, the acceleration is the second derivative. Okay, so if we're going to do that, we need to take the antiderivative again. Okay, so I'm going to look at my position function, which is often called s of x, okay, in physics. So this is the actual function f of x, okay? So when I take the antiderivative of minus 9.8x, right, I'm going to get minus 9.8, and I know I'm going to have x squared, but I want to multiply by the reciprocal of that, okay? And then I have my plus c. Okay? So my position function, right, which is my actual function f of x, is minus 4.9x squared plus c. Okay? So I'm going to use again, the information given in the question to figure out what c is. So it is dropped from the top of the tower 450 meters above the ground. Okay? So at the start, right, at time 0, then my answer should be 450. Okay. Right, this is telling me that f of 0 is 450. Okay. So I get f of 0 equals c, right, or 450 equals c. So my final function that tells me the position, f of x, is minus 4.9x squared plus 450. Okay. All right. So I am going to go ahead and copy down those 3 functions that we found out. Okay. And then we're going to go ahead and answer parts B and C of this question. Okay. So we have the acceleration function, right, which is the second derivative, being minus 9.8. We have the velocity function, which is the first derivative, being minus 9.8x. And we have the position function, which is the original function, being minus 4.9x squared plus 450. Okay. All right. So then let's go ahead and look at what parts B and C are going to ask us. Okay. Okay, when will the stone hit the ground? Okay, so in this example, when we have hit the ground, this means that the height, right, should be 0. Okay, so we'll plug in 0 for height. Okay, and then we'll solve for x. Okay, so I have that x equals plus or minus the square root of 450 divided by 4.9. Okay, so the approximate answer here is going to be 9.6 seconds. Okay. So what does part C ask us? Okay, so with what velocity does the stone hit the ground? Okay, so we are going to be looking at the velocity function v of x, right, which is the first derivative f prime. Okay, and again, when we talk about it hitting the 0 or hitting the ground, right, this is when s of x equals 0. And we just found out that that's when x is approximately 9.6. Okay, so we are going to look at the velocity after 9.6 seconds. Okay, so this would be minus 9.8 times 9.6, which is approximately 94.08, right, with a minus. So remember, the minus sign on velocity means that the rock is moving downward. Okay? All right. So the last thing I wanted to point out about this example is when you see the classical mechanics equation where it gives the position of a falling object as this number minus 4.9 t squared plus v0t plus s0, right, where v0 are the initial velocity and s0 is the initial position, right? This is exactly how you get this formula. You take the acceleration and you do 2 antiderivatives to get the position function. Okay? I hope you guys find that interesting when you see it in your physics class, and I will see you in the videos about 5.1.